So Newton's first law is often called the law of inertia. The common way to say it is that an object in motion will stay in motion, an object at rest will stay at rest unless acted upon by an outside force. I prefer to think of it as an object will maintain its initial velocity unless object experiences a net external force. So we are going to have to talk about net external forces a lot in this section of the video. So first let's talk about inertia. Inertia is the resistance of an object to change, and the main way we talk about inertia is actually through mass. Mass is the measurement of inertia, and in chemistry we called it the measurement of matter. Mass is symbolized with an M, and the unit is kilograms. So we have to be a little bit careful with our M's now. So if we have 25 M or F equals MA, we need to be careful about which M we're using. When we have a number followed by a letter, the letter is almost always a unit. So our unit M, our unit little m, is meters. So this is representing meters. When we have an equation, so some sort of lots of letters put together with an equal sign in it, this m represents mass. So we have to be careful with what unit we're thinking about. The other confusing thing about kilograms is in all of our other situations, like say we have centimeters or kilometers or hours or minutes or milliseconds. In all of those situations, we want to remove the prefix of our unit and get it into our standard SI unit. But because a gram is so small, it's not practical to use grams as our SI unit. So kilograms is instead our SI unit. So long as everything is in kilograms, we're fine. And just for a reference, a single gram could be the size of a single grain of rice. In my school, we use paper slips as hall passes, and the hall passes are roughly 1/4 the size of a standard letter size piece of paper, or if you're in Europe or some other country that uses the A systems of letters, is roughly an A4 size. So it's roughly the A4 size. A student of mine put that on a scale one day and it came out to be almost exactly a gram. So that little strip of paper is a gram. So it's not practical to use it. So we use 1,000 grams as our standard unit of mass, and that's about the size of a textbook. So what is a force? A force is a push or a pull, and there's two types of forces that we can talk about. We can talk about contact forces, which is the force on our object from something that's actually touching it or in contact with it. Or we can have non-contact forces, such as the force of gravity, or the forces between magnets, or the forces between electric charges. All three of those things are non-contact forces. But be careful with non-contact forces. They only come from certain things. So they come from magnets, they come from gravitational forces, and they come from electric charges. If we have a more typical object, such as a table, a chair, a rope, a chain, anything that's more physical, those things can only exert contact forces, which means the only time that they can have a force or influence our object is when they are physically touching our object. And we talked about this a little bit with projectiles. When we throw something in the air, the only time we can influence that object is when it is physically touching our hand. The moment it leaves our hand, we cannot influence anymore. We cannot cause it to accelerate. We cannot cause it to have a force. Once it has left our hand, the very moment that there's any space between our hand and our object, the only force that can act on it now is the force of gravity. We cannot have any force on it. So let's talk about what external force is versus an internal force. An external force is a force from outside our observed object. And if we're observing several objects at once, we call that a system. So for example, if we have Sigmund pulling on not only this one box, but one box on top of another box, we might choose our system to be both boxes together. An internal force is a force between pieces of our object or several objects within our system. So for example, if we have Sigmund sitting on an inner tube on some water, then if we choose just Sigmund to be our object of observation or our system, then one external force would be the force of the inner tube pushing on Sigmund. However, if we choose our system to be Sigmund and his inner tube, the force on Sigmund from the inner tube is now an internal force, and we don't need to worry about internal forces for Newton's laws. We're really just worried about forces that are coming from outside our system. So an external force now would be the force of the water on the inner tube and Sigmund, or the force of the wind blowing on Sigmund and the inner tube. What if we're observing Sigmund pulling a box with a rope? Most of the time, we just use the box as our system. So our external forces in this case would be the force from the rope. Notice I did not say the force of Sigmund pulling on the box. Sigmund is not actually touching the box, and because Sigmund can only exert forces through contact, Sigmund is not pulling on the box himself. He's pulling on the rope, and the rope is pulling on the box. So depending on how picky your teacher is, you might want to be careful on how you answer questions like that. What if we had before, we have another box on top of this box here? If we are again talking about the two boxes as a system, any friction between these two boxes, between the two surfaces of the boxes, would be an internal force that we don't need to worry about. We need to worry about the entire mass of both boxes, but we don't need to worry about whatever forces are keeping those boxes in contact with each other, unless the problem specifically says so. So now let's talk about net force. Net force is the resultant force of all of the forces, all of the external forces acting on our system or on our observed object. And remember, resultant is when we take several vectors, add them head to tail. Our resultant is from start to finish. So if we have, say, several forces, F1, F2, F3, then our net force is that light blue arrow in between. And there's two different ways to write net force that are commonly seen. One is F with a subscript net, and the other is with a sigma F. I prefer sigma F because of what it implies to me. So sigma means take the sum. So sigma just means sum. It means add up all of these things. So in this case, sigma F means add up all the forces. And we would do that just like we did with the dark blue forces up above. The reason I don't like F net with the subscript is because to me that might be confused for a real force. So all of these dark blue forces have some sort of object causing the force. So F1 might be from a rope. And then F2 might be from Sigmund. And then F3 might be from the Earth because of gravity. All of those have a source. Sigma F, or the net force, does not have an actual source. It's just the result. It's the force that we observe, we're able to observe from all of the interactions of the other forces. So to summarize, Newton's first law is that forces change motion. We've already seen that. So anytime there is an acceleration, that's a change in the motion. Forces cause change in motion. Forces cause acceleration. The second part of the first law, no net force is needed to maintain motion. That's the tricky one, because we've all observed something rolling on a carpet or on a rough surface. So something rolling on a carpet or on a rough surface eventually comes to a stop, and we think that we are observing no force on that object. But that's not the case. What we are observing is the force of friction opposing the motion. So friction is pushing our object the opposite way of its velocity. And if this object is just rolling with no other forces, then our net force is only the force of friction. And since the force of friction is not zero, then our object accelerates. If we instead push our object an equal amount, then we have our net force equals the force of friction minus our push. So our net force is zero, and it will maintain a constant velocity. So no force is needed to maintain motion means that the net force is zero in order for us to maintain motion. If we have a net force of zero, we will have the same motion.